introduce Lab 1. This lab investigates charged objects and their interactions. Their interactions are manifested as electrical forces, and we're going to investigate this relationship in both microscopic and macroscopic perspectives. This is the model we're going to use in today's experiment. It's a float tape model. In this model, the most important parts are these two charged tapes, tape A and tape B. These two tapes are charged by pulling them off from a third tape quickly. And after pulling them off, we discovered that the two tapes are attracted to a negatively charged pen. This means that the two tapes are both positively charged. And then we stick the two ends of one of these tapes onto two neutral objects, just as this figure shows. We're going to treat tape B, which is the tape that we stick on the neutral objects, as a system. And we're going to treat tape A as surroundings that provide charges to affect this system. To investigate the amount of charges on the tapes, we're going to use the following fundamental physical principles. During the experiment, we're going to hold tape A from below tape B and approach tape B. At some point, we'll observe that tape B begins to float and enter an equilibrium. And in this state of equilibrium, the system B, tape B, is affected by its own gravity and the surroundings electrical force. By Newton's first law, we know that in this equilibrium state, the electrical force equals the gravity, which means that mg equals to kq1q2 over r squared. And thus we're able to get the values of the charges by plugging in the other known values into this equation. And of course, we need to make some assumptions to make the analysis I made just now sounds reasonable. First, we need to assume that the air resistance is negligible. And second, we would need to assume that the net charge on the tape is a point charge that concentrates at the center of the tape. And third, we need to assume that the two tapes have the same net charge because they are prepared in the same way. By plugging the values, we find that the electrical charge on each of the tape is 1.39 times 10 to the negative 8 coulombs. And the number of electrons, which is also deficient, meaning that they are positively charged. The number of electrons deficient is 8.7 times 10 to the 10th. And ratios of the number of electrons deficient to the numbers of atoms on the sticky surface is 2.07 times 10 to the negative 7th. And thus, by now, we have successfully analyzed the electrical properties of the charged tapes in the experiment. We can also construct computational models as other ways to carry out our experiment. On Glow script codes, for example, we first initialize our constants used in this experiment, and we secondly define our tapes into coding languages. Third, we get our gravity of the system. And at last, we use Newton's first law as well as the Coulomb's law to write an equal sign between the force of gravity and the electric force. And from there, we can get our charges. And in the end, we can also use a function from lab 0 and calculate the electrical force by calculating the electrical field as a way to verify our answers. And here are the results I get back from this model. They're the same from our hands-on experiment. The magnitude of charge is 1.39 times 10 to the negative 8 coulomb. By using different assumptions, we can construct another computational model that assumes the tapes are line charges. And because we have different assumptions, this model gives us different results in the end. This model gives us a magnitude of charge equals to 1.54 times 10 to the negative 8 coulomb. Of course, we can see potential sources of errors. For example, the tapes are too large compared to a typical CRI's point charge, and slight differences will exist between the two tapes' charges. And there are more interactions to be considered. For example, air resistant. If the electrons are negatively charged and the protons are positively charged, the experiments will have the same result since the tapes are charged in the same way and they always have the same type of charge. And as indicated earlier, the differences between the electrical charges between the point charge model and the line charge model is because of the assumptions we made. When we made assumptions about point charges, we're introducing errors by neglecting the interactions between each of the top tape atom and the bottom tape. Although we're still making this error by assuming a line charge model, it is a much smaller error compared to the point charge model. And this line charge model provides us a more accurate electric charge value. Thank you for watching.